Consider a mass m attached to a spring which is attached to a wall. In equilibrium there will be no horizontal forces and the vertical weight is cancelled by the normal force. If you pull a bit the mass to the right, you stretch a bit the spring, which wants to go back to equilibrium. The recovery force is minus kx, where the minus sign indicates that the force opposes the direction of the displacement. By doing this, you are doing work on a physical system. This work you do is stored as potential energy in the spring. From the definition of work, W is equal to F arrow times dx arrow. Here, because the force goes opposite to the displacement, we write W equal to minus F of the spring dx. But this work you do is the increase in potential energy, so the difference in potential energy dV is equals to W, which is equals to minus F dx. From here we get that the derivative of the potential energy with respect to position, which by the way is the gradient of the potential energy, is equal to minus the force. This force of the spring is a conservative force. It is a force that comes from a potential energy, and it only depends on the position. Gravitational force is also conservative. Coulomb's force is also conservative. Friction is not conservative. Lorentz force is not conservative. All conservative forces can be derived from potential energy, and this equation expresses the relation between force and potential energy. The force always points in the negative direction of the gradient of the potential energy. Now we can integrate to get the potential energy. B of x is the minus integral of the force dx, which is the integral of kx dx, which is 1/2 of k x squared minus 1/2 of k x naught squared. Of course, we can always choose the origin of energies where we please, so we can choose it so that the constant does not appear. To write this gradient in 3 dimensions, we use partial derivatives. This is the Cartesian coordinates, but we might want to write them in cylindrical coordinates or in spherical coordinates. That's something you need to get used to, as the choice of coordinates is going to simplify a lot the problem solving. Now we have the expression for the potential energy, and we know the relation between force and potential energy. If we let go the mass, it will accelerate, its velocity will change, and it will change its potential energy. We can write a differential change in the potential energy as dV equal to minus F dx, equal to minus m dV dt dx. Substituting dx by v dt, we get dV equal to minus m dV dt v dt, which is equal to minus mv dV. But mv dV is the differential of 1/2 of mv squared, which is not but the differential change in kinetic energy. This is the conservation of energy obtained from the conservative force, which is the gradient of the potential energy, and from the fact that Newton's law relates a force with a change in velocity. This is in fact general for any conservative force.